Hello, everyone. In this week, we're going to cover the structure and function of IPv4 or Internet Protocol v4, IPv6, and their addresses. IPv4 addresses are four-number sequences, so 192.168.0.1, whereas IPv6 addresses are much longer and more complex. So, for instance, 21DA, D30, 2F3B, 2AA, FF, FE28, 9C, 5A. As you can see, different addressing schemas here. Both types of addresses uniquely identify network interfaces that use TCP/IP on the internet. So we're going to explore the differences between IPv4 and v6 and look at the latest updates and features that come with IPv6. And as you come to understand and appreciate IP addressing, you're going to learn how they're constructed, the classes, how things are relegated, the roles and addresses that addresses play in terms of finding a way around a network. And we're going to find how many devices can be attached to a network just based on the structure of an IP address, how you can manage the structure if you're constructing a network, and how to subdivide addresses so you can meet your needs. So in the chapter you're going to read and in this video, we're going to talk about IP addressing, its anatomy, its structures, and the view from the network in a computer. You're going to be able to recognize IPv4 and IPv6. You're going to be able to describe certain limitations. And when we bring up supernetting and subnetting, you're going to be able to explain that. We're going to talk about how to obtain IP addresses and some IPv4 addressing schemes. Again, we're going to talk about limitations, as I just talked about in a little overview, the new features in IPv6, and then some of the problems you're going to face if you're moving a structure from IPv4 to IPv6. So again, as we talked about in the first chapter, computers use IP addresses as a way to uh, signify this is me, this is who I am, so that we can route messages from a source to a destination. And computers look at network addresses in terms of bit patterns. So in IP, there's three different, pardon me, addressing schemes. So at the highest level, what you're used to seeing is the symbolic scheme, or oftentimes a domain name or fully qualified name. So it could be, tryc.edu, or it could be support.com or example.com or whatever. From that, the next level is your logical numeric address, and that's your IP address. So in IPv4, you have 4 octets, so 192.168.0.1. Or in IPv6, it goes up to 2 to the 128th different addresses. So in an IPv6 example, as you see, it's a much longer address, which allows us to give every physical device a unique physical address, a unique logical address. And now down to the physical numeric, that's your MAC address. That's the media access control address that is part of every physical device. So a domain, oftentimes you'll use the word domain in terms of website address, but really it's any collection of devices on a network. And you usually administer that domain as one single cohesive unit. I talked about MAC addresses, so media access control. So when we look at the OSI model, that's the data link layer, that's your physical address. And then ARP, that's your resolution protocol or address resolution protocol, and that translates an IP address into a MAC address. Reverse ARP is going backwards. It translates a MAC into an IP address. And an intermediate host is a computer or other device that will relay your network traffic from the origin to the destination. I also want to bring up, and we'll go back to basics a second. Remember that ultimately this all gets converted to binary numbers. So when we talk about subnetting and supernetting, These are bit masks, so it's good to review your base 2 binary numbering scheme. Make sure you understand that. And when you think about how these masks are applied, think about them in terms of bitness or in terms of binary. Um, and again, the octets, so oftentimes I'll say the word octet, that is each byte of an IP address. So there's 4 within an IPv4 address. So just remember that as we go through. So in IPv4 addressing, it's a numerical address. Dotted decimal notation is the official way to call it. So you have n.n.n.n. Each number is an 8-bit number or a byte called an octet, and you cannot duplicate them. Each address should be unique. So for instance, if you try to manually assign an IP address to a computer and another computer is already using the address, you're going to get a message stating um, that the address is taken and you're going to have to generate another one. But most networks oftentimes use dynamic host configuration protocol, so that's automatically assigning an IP address. And if there happens to be a conflict, the DHCP server, if it's configured properly, will handle that conflict itself. And again, we'll mention decimal and hexadecimal. Don't confuse them. Remember, decimal, that's our normal numbering system. When you've learned math, that's base 10. Hexadecimal is base 16. Octal is base 8. Binary is base 2. So as we go through, please remember that. And IPv4 address classes. So remember your IP addresses. It's n.n.n.n. But you have your network part and your host part. And IP addresses are subdivided into 5 major classes. And what we're really concerned with here is class A through C, and that represents the number of available IP addresses. So class A, you'll part of the first octet, the first digit will be assigned to the network itself. Oftentimes, a class A, the network will be a country or an economic region, and then you have the last 3 octets available. So you're talking, I think that's 16 million available addresses. So again, the United States might be issued X Class A addresses. Luxembourg might have 1 Class A address, but typically these are regional based. Class B, that's where the first 2 octets are dedicated to a unique identifier of the network itself, and the last 2, the host octets, are for individual devices on that network. You can think of that as almost um, a level that an internet service provider like a Comcast would use. So Comcast might have a couple, and AT&T might have a couple, and so on and so forth. Class C is the first 3 identify the network, and the last octet represents the host. And oftentimes you'll see this attached to a specific business, for instance. So in a Class B, there will be around 65,000 available addresses. And in Class C, you're going to have 254 available addresses. Again, we're not counting in that number 0, the 0th address and the 255th address. We're talking about named devices. D and E are special. D is used for multicast communications, and E is experimental only. So again, I bring these up, but when you're asked questions, we're really talking about classes A through C and the number of available IP addresses. So there's other special IPv4 address. So when I said, for instance, a class C, I'm talking about 254 available addresses. Well, because some of them represent networks. So for instance, a network address is IP address where the host bits are 0. So for instance, if you had a home network, 192.168.1 as your network address, and I put a .0 after that for its 4th octet, that would represent the network itself. A broadcast address That's an address where I send a message, and all hosts on a network must be able to read that broadcast address. And oftentimes, broadcast traffic won't escape the host or the network itself. So, for instance, if I send a broadcast and I'm on my IP address is 192.168.0.26, it's not going to escape my specific Class C network that I'm running. So broadcast packet structures. Um, IPv4 broadcast packets have two destination address fields. One is for the data link layer destination address, and one is for the destination network address. So just keep that in mind with broadcast packets. So for instance, here's a DHCP bootp packet that contains a broadcast address, and you'll see both the destination data link address and the broadcast address. Also, when you're thinking about broadcast packets, multicast packets and addresses, the host will listen on the multicast and broadcast addresses besides its own. And an IP gateway, that's a router or another device that forwards traffic to the physical network for the host. We mentioned ICANN in Chapter 1, the Internet Corporation for Assigned Names and Numbers. Um, that organization allocates multicast addresses. So again, here's another example of an OSPF packet that contains a multicast address. And you'll see further examples of these in the text. So when we talk about broadcast packet structures and we convert between IP and MAC addresses, here is a figure that exemplifies how to convert that address. So when we look at that first octet, um, how that number is translated, and when we look at the last three octets, that is how the packet structure um, and the address is converted from IP to MAC. So IPv4 networks and subnet masks. So a subnet mask is a bit pattern. When I talked about binary and we talked about the various octets of an address, it's a bit pattern that blocks off a network portion of an IP address with an all ones pattern. So for instance, we see here class A, B, and C address types, the various network layouts, and what the subnet mask would be. So for instance, a class A network, your default subnet mask would be 255.0.0.0. That would translate into a bit pattern of 1111.1111 dot 80s.80s.80s. Class B would be 81s.81s.80s.80s. Class C would be 81s.81s.81s.80s. So that would be, again, it's a bit mask pattern that represents a network. So here on the table on the left side, the network bits, that's your CIDR representation. And the equivalent subnet mask in the second column, the number of subnets, the number of hosts. So remember, these are bit patterns that are representative of the networks. So subnetting, again, it's taking bits from the host portion and you're subdividing a network even further. And then in supernetting, you're creating a larger space. So you're stealing bits from the network portion in order to make the network a little bigger. So there's a couple subnet masking techniques. So you have CLSM or constant length subnet masks. This is what most people think of when they think of subnet masks. So oftentimes when you hear subnet, it's going to be CLSM. Um, the variable length subnet mask is subnetting across a class boundary. So this is subnetting a subnet, for instance. So it's a protocol oftentimes used by routers in network environments, and it supports network extended network prefix information. And again, in VLSM, different subnets might have different extended network prefixes. Um, if you don't want to do this by hand, you can obviously find a bunch of stuff on the internet. I talked about CIDR before. Again, how CIDR plays into the bitness when you're looking into an addressing scheme and a wildcard mask. So here's a couple examples of calculators you can find that are available on the internet. It's also good to note that supernetting itself is a form of CIDR. And if you don't recall what CIDR stands for, it's classless interdomain routing. Um, but again, if you don't want to do this by hand, there's tools available. So limitations to CIDR. The network addresses must be contiguous, so they have to be next to each other. And then when you do address aggregation, your CIDR address blocks, they work best when they're in sets that are greater than one, or equal to some lower order bit pattern that corresponds to all ones. If you try to do fancy things with CIDR, not all equipment is going to be able to handle this properly. And oftentimes this deals with Class C addresses. So if you're going to use CIDR on a network, you need to make sure that the routers understand not only CIDR notation, but if you're gonna do some very specific CIDR addressing, you need to make sure the routers understand it and are able to handle it. So public versus private IPv4 addresses. Private IP address ranges are in the form of network addresses. You might masquerade some addresses. So boundary devices may masquerade certain addresses on the edge, and those include proxy servers. And then with private IPs, you're going to have some limitations. Some services require a secure end-to-end connection, and if you're using private IPs, this may be an issue. When we talk about private addressing, you'll often hear SOHO, small office, home office. Um, these use private IP addresses behind NAT or network address translation. That's the masquerading. When I discussed that word, that's what it is. So essentially, in your house, you might be issued a single IP address by your ISP, but you may have 20 devices at home. So instead of using maybe 79, 48, 126, 52 as given to you by your ISP, that is translated to maybe a private IP address space of 192.168.1.0 for your local network, or 192.168.0 WAC 24 for your local network CIDR. And that will be converted at the router to the public IP address when communicating with outbound services. So as we're talking about that, just remember that that's what we're referring to as network address translation. When we talk about IPsec, so I said some IP services require secure end-to-end connection. IPsec is an example. You can't use traditionally IPsec with NAT because the private addresses can't be translated and routed to the internet. I mean, there's a way around this. You could establish an IPsec tunnel directly between two computers, establish it from perimeter device, and then forward those packets on. But typically that's done firewall to firewall and only applies to this particular link. Standard traffic to and from the internet would go through a NAT translation. So just remember that. And then lag time is also an issue when you talk about name to address resolution. So example, you have eBay or Amazon. If you had to wait 72 hours to people send and receive traffic on the internet because of name to address resolution. We would lose a lot of money. So, we need to make sure that we have to minimize the lag time when we translate those addresses. So again, here's an example of the host I mentioned earlier, class ABC, number of private hosts available for each. So you have your class A's, your class B's, your class C's, number of available networks, number of private hosts available. So public IP addresses, super important for identifying servers that need to be accessible to the internet. Most organizations need a public IP addresses for usually only one or two classes of equipment. You need for any equipment that people on the outside of the network need to access. So servers that are designated to be accessible over the internet, or any devices that need to be open to the internet. That's where you need the public IP addresses, and usually the rest is put behind a NAT. So you can also manage access to your IPv4 address information. So you have the concept of reverse proxying. So a proxy server, um, uh, you can front for servers inside of the boundary. So you can sit in front of it and handle that communication. And then a proxy server, it provides an important service. It allows you to manage the source addresses that appear in outbound packets that pass through it. So again, if you want to keep some information private, you can still do so. And it's completely valid to use a NAT as part of a network security strategy, but it's recommended that you use multiple methods of security besides a NAT. And a reverse proxy is a good layered security approach to that. So we talked about obtaining public IP addresses, and it's it's a little bit of magic. So normally you get IP addresses from your ISP, but your ISP just can't issue any IP address that they want. IP addresses have to the ultimately someone has to request IP addresses from ICANN. ICANN manages all the IP addresses, the protocol numbers, and the well-known port addresses. So blocks of IP addresses, you have to request those. And then we mentioned IP renumbering switching addresses on every machine. They use an address from an old ISP to a new one. That's called IP renumbering. So IPv4 addressing schemes, there needs to be specific schemes. There's a there needs to be strategy in terms of allocating IP addresses. And as we talked before, there's two groups for evaluating an IP address range assignment. You have your network space and your host space. So we talked about those before, but just to reiterate. So the network space. An IP addressing scheme has a number of constraints. The number of physical locations, number of network devices, amount of broadcast traffic, availability of addresses, and delay. These are critical factors that constrain the schemes itself. And this set of constraints, it determines the number and the size of specific networks. Now there's a second group of constraints. Well, we'll continue on this first. So in terms of switches, you have ASICs, so application-specific integrated circuits. This is a set of hardware used by switches to make decisions. On layer 3 of the OSI model, it implements the logic from the software into its own ASICs, and you can partition large networks into smaller subnets. So there's a second set of constraints that helps us determine how we're going to choose what IP addresses go where. First, we want to always minimize the size of the routing tables. We want to minimize the time required for a network to converge. So for routing tables to be updated when topography changes. And then we want to maximize flexibility and facilitate management and troubleshooting. So again, we want to make sure when we're building out our networks that we follow these constraints as well. And then I guess another point, the time it takes to route between two networks, it's affected by the size of the routing table. So when we talk about minimizing the size of the routing table, the larger the table, the more time it takes to search through it. So we want to look at route aggregation or using summary addresses, and we want to reduce the number of routes in the routing table. So just keep that in mind. So the host space. Um, we want to group devices into binary boundaries because it helps us reduce broadcast traffic, avoids readdressing issues when layer 3 switching is implemented, and it helps when applying quality of service or similar policies. And it makes the creation of firewalls rules easier. There's a bunch of benefits here. Um, you want to plan for the growth of networks. Um, it's always something you need to consider. So, why should you use these boundaries? You might want to implement switching, um, apply quality of service, apply firewall rules. Um, you also need to remember one of the important things that go along with an organized host space and network address stream is documentation of the network. We're not going to go through proper documentation in the class, but when you're building or designing a network, you want to make sure that you have a logical and organized network. You're able to document it. You're able to communicate to the people that follow you. So again, here's just an example of how a network host space might be defined. If you were documenting it, maybe you would put print servers. You would have two of them using addresses 19 and 20. 10 application servers between 21 and 30, printers, DHCP clients, so on and so forth. So just an example of how you might set up a network in a logical fashion. So here is that host space that is shown in a diagram, how everything might connect. So the end of IPv4, IPv4 is dead, long live IPv4. As network use kind of exploded, smartphones, everything has a network connection now. A bunch of IP addresses were purchased, all these Class A addresses, and we're running out. So we've run out already. Um, there's still a bunch of unused host addresses. Um, Oftentimes you'll rent, like for instance, when you get home internet, you essentially rent an IP address if they issue you a static address. And even if it's a dynamic address, you can think of it as renting. You're allocated it for a certain amount of time. Um, if you're behind the NAT, it really doesn't matter because you can use whatever you want. You just need that single IP addresses. But IP address, we still run into the problem that pretty much all of the addresses are taken. um, you can purchase companies at this point. Like, for instance, if your company has an IP address block and my company wants it, I can, by purchasing your company, I can gain access to a larger set of IP addresses. You can see this in consolidation of ISPs. Oftentimes, this might come into play during the purchasing process. But again, this is where IPv6 comes in because we really have run out of space for new IP addresses. So, IP version 6 provides a vast abundance of IP addresses. This makes IP addresses no longer a commodity that you need to purchase. But again, it is a bit more complicated. It's not as easy to remember. But those are the very few negative aspects of it, the positive aspects of it. Um, every device can have a public address. It eliminates the need for network address translation. It modernizes support. It's secure by design. IPv6 is really a superior um, way to go. So we talked about RFCs in chapter 1, RFC 5156, special usage for IPv6. Um, because IPv6 is newer, it's good to keep up on RFCs, keep up on the latest changes in the standards. But just to harken back to the process for designing it, it all goes back down to RFCs and the main organizations that define these open standards. So IPv6 addressing, 128 bits long. There's a string that uniquely identifies one single network interface on the global internet. It contains a network portion and a host portion, like IPv4. And the network and host portions depends on who's looking at them and where they're located. So the format and notation. IPv6 is in hexadecimal and it's broken up slightly differently. It's four 16-bit numbers. They're called words, separated by a colon. You can see some examples below. Also uses a network prefix, and this is similar to CIDR. So we have a couple examples that describe the subnet portions below. But again, this takes a look at the bits and then breaks it down into various subnets using a similar syntax. So the scope identifier. The scope identifier is a 4-bit field. And later on, we're going to review multicast addresses, but for now, addresses in IPv6 use a scope identifier. It limits the valid range for multicast addresses to define the portion of the internet to which the multicast group pertains. So just like an IPv4, IPv6 also requires that every network interface has its own unique identifier. So although IPv6 specified that interface identifiers followed the modified EUI 64 format, software makers use the privacy format in RFC 4941. So this is an interesting problem. What vendors follow what standards, and it's common in the networking industry. So just something to consider that when we talk about so the software makers versus the hardware makers, which standard do you follow? What becomes the overall standard is important. The right-hand portion of your IPv6 address is based on the computer's MAC. It can be, and that poses a security concern. So keep that in mind as well. So interface identifiers, the bit 6 and bit 7 values. So these two bits allow you for 4 different interface identifier meanings. So if bit 6 is 0 and bit 7 is 0, it's locally unique to the individual. If bit 6 is 0 and 7 is 1, it's unique to the group but local. Bit 6 is 1, bit 7 is 0, it's globally unique but to the individual. And if both bits are 1, it's globally unique to the group. So native IPv6 addresses and URLs. So a typical URL contains the colon character, and it can be confusing when studying IPv6 addresses. So RFC 2732 describes a method using square brackets to express IPv6 addresses in a form that's compatible with HTTP URLs. So for instance, if you want to specify the port in a URL using a IPv6 address, At the bottom here is an example. So you're specifying um, HTTP, but it's going to be on port 70. So you enclose the IPv6 address in open and closed square brackets. Then you put the colon to represent the port you're trying to access, and then you put the port. So just an example of how to handle IPv6 and URLs. So there's various address types. Um, so you have unspecified addresses, loopback addresses. So unspecified addresses is all zeros. You can just put 2 colon characters in the notation. A loopback address, if you remember from IPv4, that's 127.0.0.1, and IPv6. It is just 1. So you can set the loopback address in IPv6 as well. Multicast addresses, again, you're trying to send a single message to multiple hosts. And remember, IPv4's broadcast addresses, they've been replaced by multicast addresses in IPv6. You have anycast addresses, so packets go to the nearest single instance of that address. Unicast addresses, you're just sending it to a single network interface. Aggregate global unicast addresses, you can combine other addresses into a single entry in the router table. Your link local address is the first 10 leftmost bits, set to 1111, 111010, and your site local address is 1111, 111011. I don't think you'll remember that. You'll probably need to reference it, at least for now. Hopefully by the end of the course, you'll have remembered that. And then you have your address allocations. Remember IPv6 pre-allocates only about 15% of the available addresses. Um, so your network service access point, it's 1/128th of all of the IPv6 address space. Your unicast and anycast addressed allocations, and your multicast allocations. Again, it's all IPv6 addresses beginning with 0xFF. So remember FF in hexadecimal. And I just wanted to show a table of the IPv6 address allocations as well. So you can reference this table, obviously, when there's questions related to the allocations. So some considerations for IPv6 addressing and subnetting. IPv6 in general doesn't require subnetting, but it's possible. And then again, if you're going to subnet, the extent to which you're going to subnet depends on the length of the prefix. And how you apportion the host addressing really depends on the prefix length as well. And transitioning between IPv4 to IPv6. There's a bunch of different technologies that can be used and techniques. So Teredo tunneling, ISOTAP. If you're unfamiliar, it's intrasite automatic tunneling addressing protocol. 6-to-4 is another form of tunneling. IPv6 rapid deployment, or 6RD, and NAT-PT, so network address translation, protocol translation. All of these are being used to help transition networks to IPv6. So if you get involved in a project to transition a network, these are the technologies you would use. Or if you're trying to link from an IPv4 to an IPv6 network, these are the technologies you would use. So in summary, we talked about IP addresses. These are the foundation for network interfaces on TCP/IP. IPv4 addresses, 5 classes, A through E. It would help if it said A on the slide. There you go. But we're really concerned with A through C when we talk about these addresses. CIDR, again, just a way to define boundaries and subnets. It's an easy notation as well when communicating blocks of IP addresses. Subnetting, allows additional bits to be taken from the host portion of the network, whereas supernetting takes it away from the network portion. When we talk about address masquerading, address substitution, these are techniques to hide internal network IP addresses. So when we talk about network address translation, or NAT, probably what you have at home, that's what it is. And then within all the major IP address ranges, the IETF has reserved private names or address ranges. ICANN is the authority for obtaining public IP addresses, and we have run out of IPv4 addresses. IPv6, the wave of the future is now. But remember, we are and you know, there's, let me back up. There are security features built into IPv6 that make it a very good option to move to if you have the capability to do so. But it does introduce changes in how communication happens, and you have the additional problem of translating between IPv4 and v6 that you're going to need to take care of. But there's a number of improvements. There's three types of addresses: unicast, multicast, and anycast. You have two private or local use address schemes. And again, the prefix lengths define the number of bits, apportioned to the network address and to the host address. And then again, be familiar with the technologies for IPv4 to IPv6 translation. So Teredo, ISOTAP 6to4, 6RD, and NetPT. So that's it. Again, if you have any questions, please let me know. This, again, was just an overview of the content that you will read this week and take a lab on and a quiz on. But hopefully this was informative. Let me know if you have any issues, and I will talk to you next week.